Well, it's the top of the hour. So greetings, everybody. We're going to go ahead and get started, and want to welcome everybody to American Segmental Bridge Institute's monthly webinar series. We have a really good presentation for you today, talking about the design and erection of the Selmon West Extension project. My name is Timothy Berry. I am not Greg Freeby. I'm actually filling in for Mr. Freeby today, who was unable to make today's webinar. I'm a member of ASBI. I've been a member for more than 20 years. I'm the current grouting committee chair, and I have more than 20 years experience in the segmental bridge industry and the construction management side in numerous projects across the country. I want to make a couple of announcements before we get started. Our May webinar is scheduled for May 25th, same time, and it's going to be talking about the methodology for risk assessment for post-tensioning tendons, and be performed by Dr. Glenn Washer of the University of Missouri. So hope everybody can join us for that one as well. Also, I want to announce our 2022 convention and committee meeting scheduled for October 31st through November 2nd. We're going to be in Austin, Texas this year. A great opportunity to meet all the members of this the segmental bridge industry. So also mark your calendars for that. And we are also very excited to announce we are going to resume our construction practices seminars this year. We have not been able to hold one since 2019 for obvious reasons, but we're gonna come back this August and restart our in-person seminars. We're gonna be in Seattle, Washington, August 15th through the 16th. These seminars are a great opportunity to learn basically segmental bridge 101, top to bottom from the construction side. It's a great learning experience for people new to the industry, and also an opportunity to meet a lot of segmental bridge industry experts who put on this great seminar. So mark your calendars for that one as well. As we would also like to announce, we have a new publication out there, Guidelines for Design and Construction of Segmental Bridges for Rail. This first edition launched in March and available on the ASBI website under the publication tab. And of course, all this information is available on the ASBI website if you need any more information. So for today's webinar, just a few instructions. If for whatever reason you do lose your connection during the webinar, you can just rejoin. You can pop right back in using the link that you were provided for your registration. Obviously, you will miss a little bit of content while you're gone. Just be the same as walking out of the room during a presentation, but as long as you can get back in, it shouldn't be a problem. The certificates for attendance are only issued to those who are in the meet a minimum time requirement for the session. And also for your certificates, please allow at least a week for those certificates to be emailed out to you afterwards. It does take a little bit of time to turn them around, so we ask that you at least allow a week. Well, we will be doing Q&A at the end of the presentation. If at any time during the presentation you have a question related to the information, everybody should have a little dashboard on the right-hand side of the GoToWebinar session, and there's a tab marked questions. If you have any questions, just feel free to enter them in there, and we'll gather them up, and we will have the presenters answer those questions at the end of the webinar. There is a chance sometimes we run a little bit late. We understand people may have a hard stop at the top of the hour. It's no problem if you have to leave, but we would encourage you to stick around if you want to hear that Q&A session. If you're on a mobile device, very similar. You should have a little question mark icon at the top. If you have a question, just go ahead and tap on that icon, and it'll open up a window to be able to ask the question of the panel. This is our standard slide we need to show to just to inform you that this is an educational program, and we do offer continuing education. With that, I am now going to turn it over to our presenters, let them introduce themselves and get this kicked off. So I will turn it over to Mr. Lechner.
So I'm Bryan Pickard.
Oh, sorry.
Sorry guys, just getting it all set up. I'm Bryan Lechner. I'm a senior structural engineer over at Kiewit Engineering Group. I've been in the industry for 20 years, 10 years at Kiewit now, and then my previous 10 years before Kiewit, I was over at FIG Bridge Engineers in Denver.
So I'm Bryan Pickard. I represent the owner, the Tampa Hillsborough Expressway Authority. I'm the DIA's Director of Operations and Engineering, and I've been a practicing engineer for over 40 years, providing engineering services for the Department of Transportation in Maine and Florida. I've had leadership roles at both Maine DOT and Florida DOT in bridge and roadway design and maintenance, construction materials research and testing, and construction management. I was born and raised in Maine. I received my Bachelor of Engineering degree from the University of Maine.
Okay, and then I'm Russel Dingman. I'm a project sponsor with Kiewit. Been with Kiewit for about 13 years now. Went to the University of Florida where I did my undergrad and master's in building construction. And I was the project manager for the second half of the Selmon and finished the job out. So I have a lot of firsthand knowledge. I was on the job the entire time. So this is a very exciting job. We showed a similar presentation to this out at the ASBI conference out in November out in Arizona. So we hope everybody enjoys all the content that we have here. And like we said before, feel free to ask questions here at the end, and we'll answer them the best we can.
So we'll be showing some videos here, and we have to pass it back to Tim to have sound in the video. So at this point, Tim's going to take it over.
It's an exciting day today. We've been working on this for a little over a year now. It's been in the planning for nearly 20 years.
We've gone through the design reviews, we've gone through shop drawing process, we've gone through quite a bit to get to this stage. I think it'll get people to where they need to be a lot faster and more efficiently. So I think it's really good for our area.
What you see behind me is the first segment that is going on the piers for the Selmon Extension, and it's a really exciting day because today marks real progress for the Selmon Extension project.
First segment's gone in. We're glad to see that. That's going to show the locals the progress that we're starting to make. It's going to make a big improvement when we get this project done because it's going to open up the traffic for folks. It's going to make the travel from east to west a lot easier.
So it don't look like the videos are feeding exactly as planned. So let's just move on through and we'll see if some of the others show a little better. So again, my name is Russel Dingman. I was the project manager here on the job for basically the second half of it. The Selmon West Extension is located in South Tampa on the peninsula there, connecting the southern tip of the Selmon existing expressway over to the Gandy Bridge that takes Tampa over to St. Pete. The big thing with this is now it connects the Tampa Expressway all the way from Brandon, all the way through Tampa, and all the way into St. Pete over the bridge without having to go through a red light or go through any kind of residential neighborhoods. So that was the big benefit of the job. It's a $230 million design build with original project duration of 1,000 days. As we said, the owner on this project was Tampa Hillsborough Expressway Authority. DOT did have involvement with this job as well, since we did have level 2 bridge work that was going on, and it was going down the DOT right away. The engineer of record on the job was AECOM. Then the design build team was Kiewit Infrastructure South, and then paired up with our other internal group, Kiewit Engineers Group, who helped with some of the conceptual things, looking at constructability and methods on how the project was going to be overall built and kind of the sequence of the work. As I said, the main purpose of this here was to connect people all the way from Brandon over to St. Pete and take away the heavy traffics that were on the existing Gandy Boulevard down below that basically runs through some residential neighborhoods. So now I'll turn it over to Bryan Pickard. and he can kind of give you some of the history and what led up into the job.
So this project has a lot of history, not all of it good. The Florida Department of Transportation recognized that they had a lot of frustrated travelers on Gandy Boulevard after they came over from Pinellas County into Hillsborough County across the Gandy Bridge. They went through a very congested area with a lot of shops on both sides of the road with a lot of signals that slowed down traffic. So they developed a PD&E study in 2002 that basically developed two alternatives. One was to widen Gandy Boulevard. The other was to bypass Gandy Boulevard. Of course, the bypass would have solved the problem of folks hitting traffic signals and the long delay along that route. But as a result, and you'll see in just a minute how that was problematic, there was a lot of criticism. The businesses were really concerned that nobody would be able to stop easily in their shops. And so the project was canceled due to that public criticism. Well, the Tampa-Hillsborough Expressway Authority was still very concerned about folks leaving our facility after going pretty smoothly from Brandon, wanting to get on to the Gandy Bridge. And so FIA developed its own PD&E study using a very unique design that utilized DOT right-of-way, first of its use in Florida, with an elevated structure along the median. And that PD&E study was developed in 2010, and then we procured the funding, bonding for most of it, and moved forward with the RFP with a notice to proceed of the job in 2017. So here's the bypass concept, and this was to the south of the Gandy Bridge, Gandy Boulevard, along a CSX route. It would have been elevated. It would have taken up quite a bit of private property along the railroad tracks, and the local folks are very resistant to this concept in that it would remove all of the traffic away from their businesses. The next option that they looked at was an elevated structure that was just, this one is to the north of the Gandy Boulevard, existing boulevard. In this case, it would have removed all of the shops on the northern portion of the Gandy Boulevard, and all of those shops, of course, were in major uproar over this idea. So the final concept that was in the 2010 PD&E study that FIA developed has pretty high clearance, so you can see shops from one side to the other. Additionally, it ensured that none of the existing intersections had to be revised as part of the project. Next. So as Russell pointed out, the approved alignment went along the Gandy Boulevard right-of-way. Again, it's DOT right-of-way. And therefore, as Russell pointed out, DOT had involvement in that. They had to make sure that whatever was going to go over their right-of-way was a safe structure. So the project begins at the end of the Gandy Boulevard and ends over at near Del Mabry. Go ahead. So the main viaduct was 8,000 feet long. It required independent peer review. Because of the aesthetics that we wanted, we asked that all of the folks that participated in the RFP developed an aesthetic concept that made it look pretty similar throughout, no matter what type of structure they used. In this particular case, they used a single box structure. At least that was what was in the RFP. With top-down construction, in other words, no lane or median closures during the day. All that work had to be done at night. Very limited space for the piers and foundations, and therefore the contractor is going to have to do some offsets, and did require redundant drill shafts. There were some requests that we'll be allowed to do non-redundant drill shafts with significant savings, and we refused that option. So I mentioned the high clearance. It was a 30-foot clearance, as you can see in the bottom photograph there. You can see pretty easily from one side of Gandy Boulevard to the other, and you can see how we built within the median right away with the piers. We also required fairly low height landscaping, so again, the drivers can see through and over the landscaping. This project required state-of-the-art aesthetic lighting, which we can control from anywhere through a smartphone app. So we can change colors through that app. We have any of the colors in the International Color Scheme available to us. Again, I pointed out that this fits within the existing DOT right-of-way, so 0 right-of-way had to be purchased for this project. As part of the erection plan, we required that minimal delays and no impacts to the traveling public. And importantly, I'm not sure I made it as clear as I needed to, a couple of the intersections required spans of 210 to 260 foot, which made it problematic as far as design, and so you'll be hearing more about that from Bryan. Next. So the aesthetic nature and the design of this project was so important to us that we only made price 20% of the score. Everything else, I mean, the design had a very high score, the construction methodology, the MOT, schedule was very important. 1,000 days for a $230 million project is really tight. They really have to focus on how they're going to get from A to Z in an efficient manner. So I'll turn it back over to Bryan, or Russell, I guess.
I just briefly want to talk about some of the restrictions Bryan mentioned. So the real idea here too was we didn't want South Tampa to basically feel any impact of construction during the course of the project. So from a lane closure standpoint, we had tight restrictions, very strict restrictions, where lane closure couldn't be set up till 9 p.m. at night, and then had to be opened back up by 7 o'clock in the morning. That way we take all construction out of any peak traffic times. Now, impacting the traffic alone below, we actually did not do that over the course of time. We maintained the 2 lanes in each direction throughout the whole course of the job so that they could maintain their normal traffic program or system. And the only time that we closed any lanes was during those nighttime closures. We did have some full closures over nighttime periods of time for the far east end, where we had to set the big steel tub box girders. But we had a very limited number of those that we were allowed to utilize through the course of the project as well. Another big restriction we had was with our substructure, since we had the offsets, as Bryan had mentioned there, because we had to maintain the location of the existing median and maintain all the existing turn lanes. We had some offsets. So we had post-tensioning, and I think it was about 80% of our substructure as well, to allow us to do those offsets and basically pick the location of where the piers went before the final location of the segments and the actual structure was determined. But in doing that, since we did have the post-tensioning, we had very tight windows in which we had to complete grouting of all that post-tensioning, and also waxing when we get involved with the superstructure. 31 days might seem like a long time, but 31 days is from the time that you put the first post-tension bar in that footing to the time you finish off and pour the cap. So it's a very tight window. I would say at the end of the job, we were probably averaging about 28, and that's about as fast as you can get it from when you take into account cure times and everything between segments or between sections, from doing the footing as one, the column as a second, and the cap as a final. So it was 3 pours that had to be done in that 31 days to get you up to the point, and then have strength as well to allow you to do your final post-tensioning and grouting of those substructures. Same thing with the superstructures. The sequence in putting in from one section to another, the 14 days is also very tight too, concerning the fact you're tying together certain sections and periods of time, and it kind of depends on the entire sequence of the operations to maintain that. We did maintain that throughout the entire job. We had no sections at the end of the day that weren't grouted or waxed within the 14 days allowable. now I'll turn it over to Bryan Lechner, and he can kind of go through some of the other constructability items and kind of thoughts that we provided in going into the design.
Thanks, Russell. Yeah, so pretty early on, even before the LOI and the RFP came out, we knew that there were some pretty key challenges on this job that were unique. And the first one here was our 1,000-day schedule. That's design and construction, and really it's a 1,000-night schedule. If you look at the requirements of the RFP, there's not much you can do during the day with a conventional overhead gantry type balanced cantilever erection. And really to get it done in time, we would have to have 2 headings using an overhead gantry and like a more conventional balanced cantilever erection scheme. Also, the span lengths are a bit awkward, right? I mean, it's length it's a bit too long for span by span, and really it's a little bit too short for efficient or economical balanced cantilever. But those span lengths were set based on sight distance for the left turn movements across the intersections. So all of our major crossings had spans between 210 and 260 feet, and our end spans were on the order of like 170 to 190 feet. And we also had these large eccentric foundations because of those left turn movements, and getting those foundations to fit in the median and support the loading required for these long spans was pretty challenging. And also, we mentioned earlier, there was an overhead protection plan as part of our proposal submission. That, along with an erection plan, those are pretty unique requirements for an RFP. Typically, those are I guess, produced and reviewed after you win the job. But they wanted to understand how exactly we were going to build it to ensure that there was no impacts to the businesses, to the traveling public, and they really wanted redundant support of segments anytime there was traffic underneath. So basically every single day you would have to have redundant support of the segments. And lastly, as Russell mentioned, the MOT requirements were pretty onerous, and really what it kind of came down to is you really couldn't work during the day if you use a conventional system. So pretty early on, pre-LOI, pre-shortlist, we just determined a key with that we wouldn't even pursue the job unless we could figure out a way to build this thing, in span by span. We just didn't think it'd be very economical to have 2 overhead gantries and 2 headings going at the same time. Also designed pretty early on that an Extradosed design to reduce the mass to make these longer spans possible was going to be our best approach. And then just overhead protection plan and the erection plan part of the RFP, we decided also that an underslung girder made more sense here, because those each segment, after you set the segment on the girders, they're supported positively by the erection girders, which are redundantly supported by temporary towers. There's more than 2 towers. There's 3 or 4 towers under each pair of erection girders. As we were able to achieve that redundant support of the segments before we stress all the post tensioning. And that 30-foot height really helped us here, because you don't have to worry about the cross beams of the erection girders getting in the way for overhead clearance on Gandy Boulevard. And lastly, it's pretty obvious, but top-down construction with delivery of segments from the completed structure made a whole lot of sense here as well. So what we came up with is this progressive span by span innovation, and it's essentially span by span in 2 pieces, right? So we're doing a longer span in 2 different pieces, and our temporary towers are split on the piers, spaced at about 120 feet. That varied a bit based on each pier location, but this way the erection girders didn't know that the span that was being erected was 260 feet, right? Each section being erected was your more typical 140 to 120, which is pretty optimal for span by span. Next, we erect the pier section, which is 14 segments over the pier, and stress post tensioning in that section. And those temporary towers there actually dual role, supporting the erection girders and supporting the pier section temporarily. And then without needing to advance the erection girder, we can go back and erect a drop-in section, which is match cast to the pier section. And then pour a 2-foot closure with the existing bridge that's just been completed and stress our PT in the span to make it fully continuous. At this point, the swivel crane and the erection girders can advance onward, and behind the erection heading off the critical path, we can then form up our fin for the concrete and stress the PT. And the PT and the fin is essentially just taking the reaction out of those temporary towers, so that they're actually sized initially to take half of the weight of the span out of web shear and into that fin truss there. And then lastly, you can take those towers down, advance them up. I think we had 10 sets of towers, and we always had those up ahead of us there. And that fin truss replaces the reaction by those temp towers. And Tim's going to take it back here, and there's an animation of the erection of typical span. And this is the ending video. Sorry about that, guys. Yeah, it's the computer. Yeah, there you go. I'll take the presentation back here in a second. Hey, Tim, can you give me the presentation back, please?
y'all able to see the whole video? It was, maybe I have bad connection.
Yeah, I was actually able to see it, Russell. It was
Okay, just making, it's probably my connection.
I think we lost Tim. There we go. You guys seeing my screen again?
Yep.
Yep.
Okay, awesome. Yeah, so I guess the impetus for this new structural system was the erection technique that we wanted to use that we thought gave us the most competitive chance of winning the job. And you can see here in section, the cross section actually looks like a typical 140-foot section for typical span by span. The only difference is that our webs are a little bit thicker because even though the girder itself is only spanning 140 feet between those fins, the torsion is not picked up by the fin, and that torsion represents that 260 feet of span length. So we have some pretty high shear stresses in our webs back at the support. So our webs are a bit thicker than a typical section. You can see our fin truss here. So it's an 18-foot 6 tall tower, and that fin extends the full length of our pier section. And you can kind of see there in those dashed lines, those are anchoring into delta frames inside the box. And then on the right, you can see a cross section of a typical C pier. And out of our 36 piers on the project, I want to say 30 or 31 of them were C piers. We only had like 5 or 6 fully concentric piers and foundations. And you can see there's actually two eccentricities here. That the box girder is eccentric to the pier, which is the green line, and the pier is eccentric to the foundation as well. And the eccentricity between the box and the pier was as much as 6 feet in some locations, and that was to accommodate those left turn movements at all the intersections. And those left turn lanes were pretty long. There's a lot of traffic on Gandy, so in most cases we had C piers along the alignment, and those eccentricities basically form permanent bending, moments in the piers and large loads in the shafts under concentric loading in the box, right? So there's very large moments to deal with here on these piers. And just to point out here, there is a section of the barrier that is structural. So our fin is 2 feet wide, and our tower and our barrier section here, that's in yellow, is 2'6" wide. And then there's actually a joint at the end, or at the beginning and the end of the fin, to make the barrier over the pier not structural and not part of the cross section. And that was done so that we don't suck any pre-stress loading out of the box girder at the pier. Here's a really cool cutaway that our design partners over at AECOM actually produced for us, and you can kind of see the interior workings of this thing. You can see it's really not a fin back bridge. Everyone, I guess, wants to call it that because of that fin that sticks up. It's very noticeable, but in reality, it's a king post truss. So the typical fin back bridges that you think of, like Tex Kappa, that fin is actually part of the cross section, and it extends down into it and that turns into a web inside the bridge. In this case, our fin is really separate from the section. It's not part of the cross section of the bridge. So our fin kind of behaves like a concrete tensile element. Our towers in compression, obviously, and then our bridge girder itself is the compression cord of that truss. And you can see from about this point, the center on the of the fin to the left, it looks a lot like a typical span by span girder. So you have these external tendons coming down, deviating through a deviator, some bottom slab tendons as well. And then everything to the right behaves more like this king post truss. And it really the entire triangle there rotates like a rigid body instead of getting your more typical curvature and flexure that you would see over the pier for like a typical continuous span-by-span bridge. And the big advantage of this system, I think, is pretty obvious in this animation here. So we were able to achieve a 7-day cycle at the end of the job per span. I think our average cycle per span was 9 days, and really that's nights, right? Because there's not much you can do during the day except for delivery of segments on the bridge. All the segment erection was done at night. And you see, compared to a typical overhead gantry balanced cantilever approach, and this below here is based on our Bayonne job. You can see in 30 days you can erect a 4-span unit versus 100 days for a conventional overhead gantry and balanced cantilever. So it's much faster than the conventional option. And the obvious caveat to that is you need to have temporary towers away from your piers, which is not always possible. And I think there's also some pretty big advantages here in the equipment. It's much easier to use underslung girders. They're, I'll call them dumb steel. There's not much automation to them. They're always locked. They're always have more than one support. In our system, there's either 3 or 4 towers under each girder. And it's pretty inherently stable because all the loose segments are on top. 3 points of support, nothing's hanging on cables. And then I think an important thing to remember here is that it's during segment erection, it's a pretty much determinate support for the erection girders, right? Those 2 temporary towers under the segments are taking most of the load, so you know where the load's going. And I think the major problems that we have with overhead gantries over the years is that you don't always know where the load is because you usually have 3 supports and you're moving segments and you're unloading supports and loading supports, and that one locked support sometimes can get unloaded and you have issues. And it's also for, I said on like a 1-to-1 basis, like one overhead gantry system versus an underslung truss type system, it's probably half the cost. And on this job, it would have been a quarter of the cost because we would have needed 2 headings. And like I said before, I think there's less risk of instability with this system. There's no God pin on Bayonne. All the guys on site, there's just one pin called the God pin that literally locked the entire gantry from moving longitudinally. And there was a guy, his job was to just watch the God pin and make sure it was in, installed correctly. And there's no God pin type issues with an underslung system. And then materially, there's also some pretty big advantages here. And I'd say on average, there's like a 13% savings in the concrete and in the weight of the bridge, so bearings and substructure. 16% savings on the PT. And that was for an FDOT job with wax tendons. I think the savings is probably going to be more for a grouted job where you have bonded tendons. And then our rebar and transverse PT are similar. The rebar was similar because there's a lot of rebar in the fins themselves that you would not normally have for a balanced cantilever bridge. And then on the substructure side, there's actually a pretty big savings there, and that's mainly because the permanent foundations are not supporting the overhead gantry. You don't have all that load at the offset being supported by our permanent foundations. There's no segment drop case. There's no overturning. So I think a lot of our savings came from just the fact that all of our temporary systems were supported by temporary towers in the median. And all these reductions are be compared to like a typical balanced cantilever or 30-foot span type approach. Then I want to get in here some key design decisions. I know at the ASBI conference, I forgot who asked the question, but someone asked the question, why not just use cable stays like a typical Extradosed bridge? Why the concrete truss? And our main reason for that is just the stiffness that we need to actually suck enough of the superimposed loading out of the girder. So our you can see on the right there, our goal for just dead load plus PT was half of the web shear is taken out and it's going up in that truss. And then during service and ultimate, that goes down a bit, just based on the relative stiffness between the fin and the webs of the girder. And then at ultimate, that fin cracks. So that's why there's a reduction even more at ultimate. And we did a lot of work on this front to just see where the load is actually going. And also a big benefit is that all the PT in the median, I mean, it's literally a 2'6" wide median, and any vehicular impact to those cables would be a bad day. So we actually designed the barriers to take that vehicular impact. It's a huge benefit, and also a big reason why we went with a concrete truss. And also this 3 bearing versus 2 in a tension tie. This was a big discussion early on in final design, and the idea here was just to let the load go where it wants to go down the fin tower. You know, it's 5,000 kips of load coming down this fin tower. You know, factored loading, and to have to deviate it back to our outside bearings would have required a huge tension tie in the bottom here. So we thought it was a better approach to just go with 3 bearings. We did a lot of work to bracket the design to ensure that we had the correct stiffness in the bearings and in the cap and the structure to actually predict what the bearing reactions would actually be. And the other benefit there is that this outside bearing at the edge of the C-pier cap, if you only had 2 bearings, this reaction would likely be doubled, and it would impact the design of our caps pretty significantly. And lastly, just some comments on the flexible filler and the impacts of that on our external and bottom slab tendons. So obviously, if you have a waxed type system, it's an unbonded PT situation. And what happens is that ultimately controls the PT design in the positive moment region. It did not in the negative moment region. And for a typical balanced cantilever bridge, you're going to have those top slat tendons all being grouted anyway. Even in FDOT, all the wax tendons are going to be your draped and bottom slab tendons, but it does reduce the amount of stress increase at ultimate that you can count on, and it ends up controlling your PT design and quantities at midspan. And we also didn't really have a good feel initially for what stress increases we would actually get because of this rigid body rotation of the pier truss or of the fin truss. So we actually did a push down analysis similar to like a push over analysis for seismic. We did a push down analysis and just basically like large displacement actually modeled the tendons as explicit elements and the deviators, and we allowed all the hinges to form where they would want to form. And we see that we have hinges forming at midspan, you know, in our end spans and in our middle span for loading in the middle span. Actually, negative moment hinges forming at the ends of the fins. And we were actually to measure explicitly what the stress increases were in these tendons and use that for design. Another thing to think about is that those ducts are now holes in your section for the entire life of the structure. So if you have ducts in your webs, those will never be filled with grout, and it will affect your shear capacity and your principal tensions in your webs. Same goes for your bottom slab tendons. Those will be holes for the entire life of the structure, and actually may have more controlling principal tensions in your bottom flange than in your webs. And also, if you're going to have anything supported on the bottom of your structure, so if you have props, those kind of things, those are empty holes and not grouted. So you have to take into account the loss of section there. And then lastly, one thing that I'm not sure it will ever control, but we did check this, is that it's really easy to wax an entire span of tendons in a couple hours. It's very, very fast, and the wax, you know, it is pumped in there at over 200 degrees Fahrenheit. So basically all the drape tendons, all the bottom step tendons are going to be heated up temporarily, and you're going to have a loss in your pre-stress force in those tendons of 20 to 30 KSI for a few hours. So we actually checked and just to make sure that we still met our zero tensile stress requirements for segment joints. But it's something to keep in mind is that you may want to check that in your structure. I believe that's all I have for now. I think Russell's next.
Okay, I just wanted to kind of go through some pictures, kind of explaining some of the stuff on the job, some of the things we did. This being kind of one of the first of its kind for FDOT, going with the wax system and also with the fin back system. We did several mock-ups out at our casting yard, both to demonstrate the waxing process and also to kind of show the integration with our fins. Here you can see a full-size fin mock-up that we did, fully constructed with rebar and everything, just to make sure that we understand any kind of issues or kinks that we might encounter in the field before we're actually building on the permanent structure. Also there on the right, that's a waxing mock-up simulating the waxing process through those fins as well, to make sure that we're getting the entire duct fully encapsulated with wax so that the tendon is fully protected. Next slide. So this is just some, this one in the next slide are just some pictures from our casting yard. We had 744 segments on the job. We set up with a 5-bed system, one that could do the expansion joints and pure segments, 2 that were doing typical segments, and then 2 final ones that did all the anchor segments that are the segments that tie into the fin from a timing standpoint. The anchor beds could also be converted to be used to do typical segments as well. And that's really where we optimize, going from system to system. We also had the rebar jigs set up back behind there. And I think we had 7 jigs set up so we could pre-tile our cages and set out. We had about a 10-acre site that we set up on, and we had the storage capacity of taking right up around 250 segments out on site. So here you can see towards the end of the casting operations, we were getting pretty full, but we never did actually fill the site, but we were right there at it. So this 10 acres turned out to be the right size for our 744 segments that we had to cast for the job. Next. This again is just some of the custom equipment that Bryan had mentioned for our erection process. Modified lift that also had the height to get up over top of our fins for transporting the segments from the bottom base all the way down the bridge over the fins into the swing lift that basically set the segments down onto the truss. That's the segment setter there on the right hand side that was fully custom fabricated for this job, that allowed us to deliver the segments up the bridge, set them down on the dunnage, and then that picked them up and swung them out onto the truss system that we utilized to launch the segments out. Next. This is kind of just an overview. You can see how at night it was all lit up and how the segments kind of looked. As Bryan said, we'd initially set the segments out. We'd roll them out from out to in. We'd build out that initial pier segment, do the initial stressing on the pier segment to tie it together, and then we would do our drop-in segment and closure pour there at the end of that prior to launching forward to the next section. Next. So this is just kind of showing again, this is the bottom anchor on the right-hand side that's showing the anchors that are in these anchor segments that are tying up to the fin backs. So pretty large systems, and then you can see on the right all the different temporary post-tensioning and permanent post-tensioning kind of going on at our pier segments on the left. Next. This is just kind of a bottom down view. These are on the right hand side, those are the towers that the truss is advanced on top of. The foundation for those was a variety of auger cast and drilled shaft, depending on the location and the weight and the capacity needs for each one. And then on the left hand side, you can kind of see the 2 trusses that were self-launching and basically initially got set onto the truss of the first span, and then we're self-launching going from tower to tower throughout the course of the bridge. In total, we had 10 tower setups, so that gives you about a 5-span length to get out in front of yourself to keep the truss progressing and to give you time to break down and then transfer these forward to continue down the entirety of the 35 spans which we erected. Next. And again, this is just another, final actual picture there on the left of the fin, so you can see the final design, the estuary design that we came up with, and on the right there, you just kind of have an in progress picture to see initial to what the final product looked like. Bryan talked about the different lighting systems. All the fin backs up top also had internal lighting inside the fins and also on the outside shooting up the fins with the ability to change colors and modify for different events in the locale, whether it might be for the local sporting teams or at holidays. Gives them a great time. Also, we did have a combination of brick pavers down there in the median and also some natural landscaping. You can see on the right there's some palms. But nothing that was too obscure that would block the views, again, going across for the local businesses. Go ahead, Bryan. Okay, so now we have our third video. This was the night that we set the last segment.
Having some struggles with this video. There we go.
So we're here on a great night for the Tampa-Hillsborough Expressway Authority. We just watched them set the last segment of about 744 bridge segments on a 1.5 mile structure. That's part of the Selmon West Extension project. We're very excited about it.
Just seems like yesterday, almost 1.5 years ago, we were at the other end of the bridge and we set the first segment. We were excited about that and how that was going to affect the community. Well, here we are now, just before Christmas 2020. We set the last segment in place tonight. Moving forward, come springtime, we're going to have this bridge open to the public.
Tonight is for everybody who dreamed of this project. Thank you very much. We're very, very excited about what you've been able to do for our city and our town. We can't wait to be on this road. Here's to everybody.
Back to you, Bryan.
So this project at this time has won 13 awards. As you can see from some of these, there's some local awards, but there's some very prestigious nationwide awards, including the Design Build Institute's one of their award winners. And what's not included in here is a 14th, which is the National ACEC Construction Award, which will be given in May in Washington, D.C. A couple points I did want to point out. This project, as I pointed out, was financed through bonding. We promised the bonding agencies that we would get 9,000 cars per day on average. 2 days after the project was opened, we had 12,000 cars per day. So we exceeded within 2 days what we promised the bond company. And last week we were averaging 21,000 cars per day. We have relocated 40% of the traffic from Gandy Boulevard. So we did achieve exactly what Florida DOT and THEA wanted to, which is to remove from Gandy the folks that just want to do the through traffic to get to Dale Mabry or through the expressway. Also,
Maybe one more video, Tim, and then
Yep.
we can take some questions.
Yep, so this is the last video kind of showing the overview of the entire project, and so everyone can kind of see the final product. And that concludes our presentation. So if there's any questions at the moment, we can try to answer those. We still have a minute or two here.
Yeah, we got a few, definitely got a few questions. Thank you guys. That's what a bunch of innovative solutions to some problems on that project. Really fascinating. So let me go ahead, and the first question somebody had was with the completion date. When this project completion, did you run into any issues with COVID impacting your schedule or impacting any part of the project?
This job did take place during COVID, so it did kind of change some of the procedures and how we work day to day on throughout the job, and did push the schedule a little bit because of COVID and dealing with that, since COVID was going on during this time. But overall, the job was very safe. We had a lot of good COVID procedures in place, and we never had really any serious outbreaks or really outbreaks in general, period, on the job that caused any major long-term full shutdowns on the job. But COVID definitely had an impact on us.
Okay. Got a question about the launching girder. Someone wondering how the segments were moved along the girder and how the elevations were adjusted.
I can answer that, or Brian, do you want to answer that?
Yeah, sure. Yeah, so there's these little carts, I'll call them, and it has a jack head on it, and there's 3 per segment, so you have 3 points to form a plane. So under one wing you have 2 of these little carts, and on the other wing you have 1 cart, and then it kind of alternates for each segment. And you can adjust the elevation using those carts because there's a jack on each of these carts, and they roll on the top of the erection girders. There's actually a track for them on top, so it's very easy to set the girders on these carts with a guess at the elevation that you're going to need, roll them down into place, and after you get everything on there, because these erection girders do move a little bit, excuse me, you then survey and set final elevations on all the carts.
So, and to add to that, it was a Hillman roller system, and the carts also had a track that the truss had a chain drive, basically winch, that would bring them out in place to bring them out to their final location. And then once they were brought out, they could be unlocked from the actual chain drive and then locked into place so that they didn't move as the other segments were being brought out.
Okay, thank you. Another question about the fins. Wondering how you decided on the height of the fins, and do you think increasing the height could have increased the bridge span length?
Yeah, so the fin height.
Yeah.
I can answer that one. The original height of the fin was kind of, it was the goal was to be around L/15 for the longest span, and that's just to match what you would typically see on Extradosed bridges, across the world. And then we also had early conversations with Deal to see what they could design us for a carrier that could get over that fin while holding a segment, because there are some crossfalls on the bridge, and those straddle lifts can get pretty unstable if they're too tall. So it was kind of a balance between getting high enough to be efficient, and also being low enough that you can actually have the segments travel over the top of those fins.
Okay. Another question about the fins. I wonder if you could discuss any, I'll say challenges or any extra steps in the casting process to account for where those fins tied, through the deck to the precast segment.
From a segment casting standpoint, or a segment, or for a fin casting segment?
For the segment casting.
We had custom formwork, metal form system, and the internals were very relative between the type 1, 2, and 3. There's 3 types of anchor segments that we had. I can't really say we had any major issues from a casting standpoint on that.
Okay. Question about the use of flexible fillers. The question is actually the reason why you chose flexible fillers. I'm going to assume that wasn't chosen, but why were flexible fillers used?
Yeah, that wasn't chosen. That was, I believe that was part of the RFP.
Yeah, so it's part of the FDOT design manual. It actually had like a design bulletin issued several years ago, but all projects moving forward in Florida are going to use flexible filler for any tendons that are not fully located in the top slab. So your transverse tendons and your cantilever tendons that are fully in that top slab can be grouted. There's not much vertical gain or fall in those tendons, and you have traffic loading over the top of you. So there's a benefit there to have a grout on those tendons. But any tendon besides those that is in the bridge, so all of your external drape tendons, your bottom slab tendons, are fin tendons in this case. If you had like a cast in place box or a post tensioned eye girder, for instance, it could be the same thing. You'd have flexible filler inside those web tendons. So it will affect the design of most post tension structures, and it did control our design in some locations.
Okay. One more. You talked about the casting yard, and I think you spoke a little bit about delivery of the segments. But with this particular site and the complete top-down requirement and no impact traffic, how did you overcome the challenges of delivering segments to the site?
All delivery was done during the day. It was a pretty straightforward track where we took, because our yard was located just on the other side of downtown Tampa, on a not a super busy, and then we actually used the existing Selmon to bring it all the way down to the site, and then everything was received in our approaches at Invent 1 and staged there prior to being brought up onto the actual bridge itself.
Yeah, I'll mention too, and the actual viaduct is 7,500 feet long, I want to say, and having to carry those segments that full length, for every segment sent would be, I think, a long time. So we actually pre-staged all of our segments on the completed bridge. So that was the design case, was checking that we can basically have 2 segments between each fin at the center of the bridge, while a straddle carrier was carrying a segment over the top. So we actually designed the bridge to support the loading of all these stage segments.
Yeah, that's a good point too. We were basically moving segments up and down the bridge 24/7 to get them all staged to allow for erection to go in the sequence and time frame we had.
Okay. Well, I think that's going to wrap it up. We're about 5 minutes over, which isn't too bad. I want to thank our presenters again. Really fascinating project, and a lot of fascinating, innovative things done to overcome some pretty major challenges. I encourage everybody, if anyone's interested, there also was an Aspire magazine article on this project, and if you look in the handout section of your dashboard, there's a link to that article as well. I encourage everybody to go read it. There's some more information about this project. So thank you again, everybody, for attending, and thanks again to our presenters. And we'll look forward to doing this again in May. So everybody have a good day.
Good, thank y'all.
Thank you, everybody.
Thank you.